6.3 Volume by cylindrical shells. Essential question: how do you represent in integral notation the volume by cylindrical shells? Compare and contrast volume by cylindrical shells with volume by discs and washers. Let's take a look at a problem where it would be impossible for us to use washers or discs. Let's see why. We are revolving around the y-axis, and we normally make our little rectangles perpendicular to the axis of revolution. Unfortunately, the length of the rectangle would be formed by the x on the left and the x on the right, and we can't differentiate that with this function. So we have to look at another method, and the other method is called the method of cylindrical shells. Cylindrical shells is actually taking the volume of a cylinder and subtracting the volume of a smaller cylinder. So we have this. So we're taking the two volumes of the two cylinders, one with the bigger radius R2 and one with the smaller radius R1, and we're factoring out a pi, and then we're going to factor this difference of two squares, rearrange it so that we write this here and introduce a 2 and a 1/2, and then put this on the end, and we're going to find that this really represents the thickness right here, which we're going to call delta R. And this is really the average of the x's, so we'll just replace this with R and we'll realize that this is just the average of the x's. So the formula becomes 2 pi R H delta R. And what's easy to remember about it is it's circumference times height times thickness. We're going to take a look at this curve that we're going to revolve around the y-axis. It's going to create this volume. So how will the shells look that'll make this volume? And it'll look something like this. These are all the shells. Some people like to call them tubes, because if you put one tube inside the other and you have enough of those tubes, it's going to make a volume. So we're going to take each one of these shells and we're going to sum them up, and then it'll become an integral. Now notice that one of the interesting things about this representation here is it's parallel to the axis of revolution, not perpendicular. Also notice the limits of integration. It starts at the very lowest, smallest part where you're starting the shell, the rectangle that will revolve around and make the shell, to the last part. It doesn't go from negative b to b, but from the inner to the outer. So pay attention to that as we continue. All right, an easy way for you to remember it is to just think of a shell as if you unwrapped it, it would be a very thin prism. So this would be the length, and the length is coming from a circumference. The height here is coming from the height to the curve, and then there's going to be some thickness, which will make that 3D thickness here, and that'll be the thickness here. Okay, so let's go ahead and start this problem. All right, delta V, and here's our standard way of writing it: circumference times height times thickness, and in this case the thickness is delta X. Now this is our radius, and our radius is really the distance from the y-axis to the curve, so we can just replace that with x. And the height is really the y of the curve. Now because delta x is here, we know that's going to be our variable of integration. So I'm going to replace the y of the curve with this. So this will be 2x squared minus x cubed delta x. And again, notice that this little rectangle that we've created is parallel to the axis of revolution. Our volume will be from the smallest, which is right here, 0, outer to the 2, and that'll be 2 pi x times 2x squared minus x cubed dx. Now a common mistake is to think of shells like we did with washers and discs. Washers and discs were like stacking things from the lowest to the upper. Now we don't want to do that in this case. You really don't want to go from -2 to 2. That's a stacking idea and not a shell idea. So common mistake is for you to go from -2 to 2 and then take this integral. All right, let's go ahead and do another problem. This problem we could do by washers, and I'm going to demonstrate that we can do it by shells as well. Delta V is equal to 2 pi r, which is the radius, I'm sorry, the circumference times height times thickness, and in this case our thickness is delta x. This is going to be our radius, and our radius is going to be the distance from the y-axis, which is x. Now our thickness is not so easy. Our thickness is going to be the y of the upper curve minus the y of the lower curve, and then delta x. Now since we have delta x, we know that's our variable of integration, and so y of the upper I'm going to replace, that's the line. Y of the lower is my quadratic, and now I can set up my volume, and remember, go from the very inner, the very inner shell to the outer, and this point is 1, 1, so it's going to go from 0 to 1, 2 pi x, x minus x squared dx. All right, let's take a look at this problem, and what we're going to be doing is we're going to be revolving it around the x-axis instead. So again, our little rectangle representation is always parallel to the axis of revolution. So delta V is going to be circumference times height times thickness. This time our thickness is delta y. Now our radius right here, how far we're going, is going to be a y coordinate. And our height, this is our height, is not so easy. So the whole distance here is 1, and this distance right here is x, and what we want is this distance, which is r, which is the height. That's what I'm looking for. So that's going to be 1 take away x, delta y. Again, I don't want to keep the x there. I want everything in terms of y, and I know that x can be written as y squared, so I'm going to do 1 minus y squared delta y, and my volume will be equal to the integral. Now all of these shells, the lowest y is 0, the highest y over here is going to be at 1. And that's what we're getting right here as our answer. Now what's interesting to note is the disk method was simpler in this case. Okay, last problem. Let's take a look at something where shells are the only alternative that we have here, and also take a look at something being revolved around something other than the x or y axis. So here's our little rectangle representation, and then it's going to we're going to make our shell there. So delta V will be equal to circumference times height times thickness. Our thickness is delta x. Now what's difficult is our radius. So let's go ahead and take a look at our radius. This is our radius. This is what we want. We know the entire distance here is 2, and we know this distance from here to here is x, because that's what an x distance is, from the curve to the y-axis. So this is our representation for r will be 2 minus x. Now our height right here will be the y of the curve, and then delta x. We don't want to leave that y of the curve there, and the y of the curve right here, here's what the curve is. It's x minus x squared delta x. Now we're ready for our volume. Now our integral, remember inner, outer. Now you can start with 2 and go to 0. It'll give you a negative number, and then we can take its absolute value. Or you can just start at the outer shell and then move to the very inner shell, and then this will be 2 pi 2 minus x, quantity x minus x squared dx. Our last slide is somewhere you can go. It's called That Tutor Guy, and he has a video in which he demonstrates the difference between discs, washers, and shells to give you a better idea how to compare and contrast.